Let's take a look at the end of chapter 6 here. This is the last section, the culmination of what we've been doing in chapter 5 and chapter 6. Alright, so 6.7 is called solving quadratic equations. I haven't really used the word quadratic yet, so I'll define it a couple ways. Just the term quadratic is alluding to the type of function we're dealing with. It's saying that the polynomial that we're looking at has degree 2. Again, that means that it has a highest power of 2. Right? If you take college algebra, we'll look at cubic functions and quartic functions, and there's a word for every type of degree there is, but for the most part, degree 2 or 3 or 4 we deal with. If we can handle those, we can handle any higher power. But so yeah, this word just references the degree of the polynomial we're looking at. But more specifically, in an equation, all right, we obviously have to have an equal sign. A quadratic equation looks like, all right, here's my quadratic piece. All right, this whole polynomial is quadratic because the highest power is 2. So I have a polynomial here that looks a lot like the things that we've factored so far. And to make it an equation, we're going to make sure that it's equal to 0. So this is an important part of the quadratic equation as well, that it's equal to 0. So, all right, all of our equations need to look like this. So I'll put down some steps to solving, and we'll do an example over here. Let's make one up real quick. We'll do 2 examples. All right, so 3x squared plus 10x minus 3 equals 0. All right, so to solve a quadratic, lots of times we learn how to solve a new type of equation. It all requires an initial setup. Okay, so the initial setup for a quadratic equation is important that it's equal to 0. I'll explain why in a second. So I'm going to emphasize that here. We need our equation equal to 0. Sometimes, as in this example, it already is set up equal to 0. This is quadratic form, so not a problem. We can go right into solving. But if it's not equal to 0, we're going to have to do whatever algebra we would need to make happen to make the equation look and take this shape. So we'll look at an example where it's not quite equal to 0, but we can make it happen. All right, once it's equal to 0, we'll take the same steps. We're going to factor the polynomial. So I left this up over here, which is just a reminder of the 4 different ways to factor, but essentially remember it's just 2. GCF, unfoiling easy, unfoiling hard, or unfoiling with a difference of squares. So there's some examples you can look at just as a reminder of those different types of factoring. But in this case, it's not going to tell you which way to factor. You're going to have to look at this and know, does a GCF apply? Is this going to be the harder version of unfoiling or the easier version? So in this case, it becomes a little more difficult because it's up to you. I'm not going to tell you exactly how to factor this polynomial. All right, so let's go over here, all right, and see which of these categories it fits under. All right, I don't see a common factor here, and I do see a coefficient out front. So if there's no common factor and a coefficient with 3 terms, that's definitely unfoiling the hard way, but it's still unfoiling. So let's break this apart. It's not a terrible situation because our initial coefficient is 3, so we have to start with 3 times 1, 3x times x. All right, our constant term is also 3, so it has to be 3 times 1. We just have to figure out where do we put these 3's and 1's to make a 10 happen in the middle. So a little bit of planning ahead here, and I think this will work out because we have our outside 3x times 3, that'd be 9x. I have to change the signs up here. That's a mistake on my part, but we can fix that easily. This problem needs, I wanted it to be this. Sorry about that. Easy fix though. 3x times 3 is 9x. 1 times x is 1x, and if we put the correct signs in here, they both need to be negative. They can both add up to a negative 10x, negative 9 and negative 1. All right, so we factored that correctly now that I fixed the problem. All right, so that's nothing new. Again, recap of what we've already done. All right, once that problem is factored, all right, we're going to set each factor equal to 0 and solve. All right, the reason why we do this and the reason why we're able to do it is because, okay, this is an equation, keep in mind. In any equation, we're trying to find a value for the variable, in this case a value for x. We're trying to find a value for x that when I substitute it in, the left side is equal to the right side. So we're always trying to solve this equation. Okay. Well, why we want it equal to 0 is because now that we've factored this, we've turned this situation where we have a subtraction and addition, we've turned it into now multiplication. So we actually have this property called the zero product property. A fancy name, but something that I think you guys already would be able to figure out on your own if I spelled it out for you. All right, what the zero product property says is if I have two quantities, right, it doesn't matter what I'm talking about, if I have two quantities that I'm multiplying together, right, and the answer is 0, right, any two things that I multiply together and the result is 0, what do I know about those two pieces? If I have two things multiplied together and the answer is 0, I know that one of those two pieces has to equal 0. So that's the same thing that's happening up here. I have two expressions being multiplied together and I know the answer is 0. Well, the zero product property tells me that either this product, either this factor has to be 0 or this factor has to be 0. So that's what we do. We take each little factor and say, well, what if this factor is equal to 0? And what if this factor is equal to 0? So that's what I mean here. Set each individual factor equal to 0. It should create two little equations that we can solve with our skills and our algebra skills we've already developed. So yeah, we can add 1 to both sides. We have 3x equals 1. Divide by 3. X is equal to 1/3. That's one answer. And we're also going to have another answer over here where we can add 3 to both sides. And x is equal to +3. Right, so it may seem weird that we have two solutions to this equation, but when we go, if you take a college algebra, we'll explain a little bit more in depth why there's two solutions. Right, but it boils down to it's actually the fundamental theorem of algebra. In more or less words, the easiest way to see it is that whatever the degree of the polynomial is, right, that's how many solutions you're guaranteed to have. There's a little bit more intricacies to that statement, but for our purposes, that's the easiest way to see it, is that, right, we're going to have at most two solutions to a quadratic equation. So, all right, there's one good example of it. Let's take a look at another example. I'll erase this one out of here. Okay, where we have to do a little bit different work, or a little bit more work. We had x squared is equal to 3x plus 28. So a little bit different. You still get the sense of this quadratic field, but the issue is that it's not equal to 0. Right? But we have the skill set to make that happen. So we can either, right, make a 0 happen on this side of the equation, which might seem easiest because there's only one term to get rid of, or we can make a 0 on this side of the equation, which might seem a little more difficult because there's two terms that we'd have to get rid of. But just from an experience standpoint, my advice is that you want to try to keep x squared positive. Right? I don't want to mess with a negative coefficient, because notice when we unfoil these things, the leading term is always positive. It just makes things a little bit easier. So I'm going to try to keep x squared positive. So I'm going to keep it here, and I'm going to get rid of these other terms on this side of the equation, getting a 0 on this side. So and we can do that in, well, we can do it in 2 steps. I'm going to add a negative 3x. out, cancel out here. These two terms are not like terms, so the best I can do is write them side by side. Now I'm almost there. Let's get rid of this positive 28 and add a negative 28 to both sides. So these are gone. And on the right side of this equation, I have nothing left, so just a 0. And again, no like terms over here. I tried to show you that they can't be combined. And we successfully turned this problem into our quadratic form. Now try to think of which way this best works out. Is it a GCF, unfoiling, easy, hard, or a difference of squares? This looks like to me, just an unfoiling one, but an easy one because I don't have a coefficient, or I have a coefficient of 1 out there. So we just need to figure out two numbers that multiply to 28 and add up to 3, or combine to get 3. And that should work out to be 7 and 4, with a negative 7 and a positive 4. Okay, we're not done once we factor when we're starting to solve an equation. We still need to come up with those answers. So we take each little factor and set it equal to 0. These little equations are simple and short, and if you do enough of them, you start to come up with a pattern, and you can probably do it without writing these little equations down, because we know that we're just going to add 7 to both sides and end up with a positive 7. Right here, we're going to subtract 4 from both sides and end up with a negative 4. Right, so it's possible to see these factors and come up with your solutions right away, but as advice and for these videos, I'm just going to make sure that you remember that what we're actually doing is solving a little equation. The equation's so tiny, and there's only usually a 1 or 2 step problem that most of us can do it in our heads. So it's a good idea to get used to doing it in your head. Most people will not write down this middle step. But okay, there's the idea behind solving quadratic equations. I didn't give you an example of every situation. I'm going to do that on the next video.